Thank you po, Miss.
Can I start sharing my screen or?
Sure po. You can take control the screen na po.
Please share screen. Okay. I'll, can I start the lecture or is there any
Yes po,
more?
Miss. You can proceed.
Let's start. Okay.
Your screen
Thanks,
is yes.
everybody, for joining this tutorial the tutorial this morning. So our topic is the principles of steel design and design for flexure. So our outline will be I will discuss about the dimensions and properties of steel and general design considerations, and we'll go through the steps in designing a flexural. And then we also do some practice, do some example calculation for flexural member design. So I will use the NSCP and the AISC manual 15th edition. So uh, this is the overview. Where we will focus on this topic, dimension and properties, general design considerations, design of flexural members. So this is our topic focus, and we'll go briefly go through chapter 17, the miscellaneous data and mathematical information, because you see AISC is in imperial units, right? So when you look at the manual, all the steel section will be in uh, feet, what do you call it, inches, feet, and keeps. So our NSCP is in metric. So that's why we need to check this chapter 17. Chapter 17 will show us the equivalent sizes of steel members in metric. So sorry guys, I might have a slow internet connection, so I'm not sure later on. If you have any question, you can just send me an email or send a chat. How guys, Aces, how if they have questions, how will they be able to
They can send their
uh,
questions in the chat box. Then
in the chat box here
yes po.
in Teams? Is it?
Yes po
I
in
don't
Teams
see.
po. Or they can
Asan ba
use
yung
their mic.
ah? Oh, okay. Meron na bang students? Asan sila? Nasa FB ba sila or nasa Teams?
Mm,
Or recording lang siya?
correct. Siguro po ngayon, wala po masyado students or siguro dahil po masyado
So
maaga.
recording,
So
okay. So
today po
recording
recording
lang.
na lang po muna. Yes po.
Okay, we'll do recording. Okay, can just continue. Well, guys, kayo na yung nakakaano. Pagka medyo what do you call this, nagputol yung internet ko, you just message me. Then I will go through again pagka malabo yung explanation doon. Okay, so let's start with the first topic, introduction and the dimension. So these are the uh, example. One is this steel section is a W. The most common type is a W shape. So the dimension that we need to take is D, web thickness TW, flange width VF, flange thickness TF, and the distance from the web. I get my. Pointer. Where are we? A distance from the web aligned to the flange toe of the way. So this is the K1, and the distance from the outer base of the flange to the point where the web fillet begins, T. So it's from here to this. That's the dimension. And next. Okay. And the material properties and notation. We need to take the moment of inertia I, plastic section modulus X, elastic section modulus S, radius of gyration R, torsional constant J, warping constant CW, and the member axis, the minor axis is along the Y, and major axis along the X, and longitudinal axis is along the, this is your beam span as along the Z axis. Okay, so for us to be able to um, understand or design the steel, we need to understand the mechanical properties under certain loading. So when you buy or when your steel section, when you take the coupon, you get a small piece of it, and then you send it to the testing company. What they will do is do tensile test. So they will elongate the section, and then they will plot this stress strain diagram. So the strain is the, strain is the deflect elongation, right? The elongation over original length. And the stress is the force, the tensile force over the area. Oops. Pointer. So the ultimate, okay, once you apply the load, the steel will, the section, right, will elongate, and this area is the elastic limit. So means you can still stress, you can apply loading to your steel, to the steel section without failure. So you will still, once you, if your stress is within this limit, the yield stress, the section will still, once you stretch it, it will still go back to its original shape. But once you continue loading or applying the load, it will reach the plastic limit, and once it exceeds the plastic limit, it will reach the strain hardening. And at this point, once the section, once it elongates, it wouldn't go back to its original point, to original size, and until it reached the failure. So here is the maximum. So that's why it's the ultimate stress. That this is the ultimate stress that you can apply on the section before it fail. Okay, so these are the list of the structural steel material standards based on NSCP. The most common is this ASTM 836 and A992. So this is the KSI. This is the 36 KSI. Wait, again. Sir. Which is equivalent to how much is it? 36 times 6, 895. 36 times 6.895. 6.895. This is the 248 MPa megapascal. 48. And 992 is the 50K, 50 KSI. 50 KSI, which is your 348. 348 megapascal. So these two is the most common section that we use. And these are the structural steel shapes. We have the W or the wide flange beam, angle, steel pipe, C channel, and the tube. Okay, so this is just how it looks like in actual. Okay, so for us to calculate the or do the design, we need to also understand how or what are the dimension and properties we need to take from the AISC manual. So this manual is in in various also in inch. This is an example. So for the the shape W16 by 100, this means that the depth is 16 inches and laser 16 inches and then 100 pounds per foot. Say pounds per foot, right? Yeah, pounds per foot, 100 pounds per foot. And so area depth. So we'll take all these later on for our design. And the properties here is in the section for this size is in section 1, that's 23, table 1, that's 1, page 34. So we need all these section properties for the design. And the section 17, table 71, so list the US standard section compared with the SI equivalent. So it will be in metric units, but only the what we call this the section description is in metric. So the rest you will have to convert. But actually, there's some you can download mobile apps to be able. So when you have this, actually I have a mobile app. I'm using a mobile app. So once you have the section, so I'll just show you. Can you see? I'm not sure if you'll be able to see, but there's one AISC structure that I use. So once I have the this shape and then the SI equivalent in is the depth, and we need the width, thickness of the flange, thickness of the web, and in x-axis and y-axis, the moment of inertia, plastic modulus, and the elastic section modulus, and the radius of gyration. Okay, so general design consideration, the beam can fail by reaching the
Hello po, miss. Sorry to interrupt.
plastic moment and becoming fully plastic, or it can fail by healthy. Yes,
I think
may na.
nagcha-choppy po.
Choppy. Saan nag-start?
Like before, dun sa slide po na SI equivalents of standard US.
So balik ako doon. Okay. Thank you.
Hindi po gumagala yung slide nyo from that po.
Ito, dito. So, okay na yan. Okay na siya.
Yes po, gumalaw na po yung pointer nyo.
Gumalaw na yung point. Pero nasa ano siya, nasa SI equivalent na.
Sa ano po, general design consideration.
Ah, bumalik ako eh. Wait, baka nag-load lang siya.
Ayun po, okay na po. Nasa
Okay na.
table
So,
na.
okay, let's go back to the SI equivalent of standard sections. So, for the you the the same example, right? You can get the equivalent to SCPO. And then oh, by the way, guys, I'm using because my 15 edition is quite hindi siya malinaw. So I'm using 14. So maybe baka yung mga pages may nabago is almost the same. And S equivalent. So the S equivalent for WCW 410149. Okay, so yeah, based on the section that we take, we can or use all the section properties. So as I mentioned, the AISC is in various units. So I suggest you can download the mobile apps. Yeah, then you can use the some mobile apps. It will be in a metric, so you can use it and it will be faster. But I think in your examination, I asked one of the professor. He mentioned that they usually give the member sex properties, so you don't need to take all these. But in your practice, when you do your actual design, uh, if you're using AISCs in imperial or in a inch keeps, so you can use some those mobile apps. Not really. Some are free, some you have to pay. So better use the free one, but it will have. So you have to be careful when you install size. So general design consideration. A beam can fail by reaching the plastic moment and become fully plastic, or it can fail by lateral torsional buckling, either elastic or inelastic. So later on, we will do a check on this, or planche local buckling, FLB, elastically or inelastically, and the web local buckling, WLB, elastically or inelastically. So if the maximum bending stress is less than the proportional limit when the buckling occurs, the failure is said to be elastic. Otherwise, it's inelastic. Okay, so requirement for compact section. Local buckling can be prevented by using established limits on slenderness ratio for various elements such as the flanges and the web member. So you check the and the web. So classify it as compact, non-compact, or slender. So we will check the length of the outer, how do you call the outstand of uh, the extended for the flange, right? The extended part of the flange, and then and also the web. And then if the flange and webs are compact, the limit state for the entire member will be reached before local buckling occurs. So means you can use the full section for your design. So you can use the plastic or the plastic section modulus. So this is the maximum moment capacity that your section can achieve. But if it's non-compact, you need to do some reduction, and it's slender. Usually, most of the ASTM sections are either compact or non-compact. we can only encounter slender section, right? If you use built-up sections, because built-up you will have to choose a steel plate for the planche, and then but this is if you do a build-up, is a expense because you need to do fabricate it will be like this. You will get for build up, so they will have a planche, a steel plate. They will use a steel plate on the planche, and then uh, it will be just like this, and then another steel plate. So you can, to be economic, then you will weld it here. Then you do a welding. So using this kind of build up sections, right, it will be more economical based on the material, but on labor, it will be more what they call more expensive, because you need to do compared to the fabricated, or those that milled fabricated section, the double section, or the hollow, the tube or circular section. It's already mass produced. For built up section, it's that you have to specially fabricate it, but it is usually used for those long span bridges, because it will be more economical. So we only do this, but in practice, we really don't want to use blender section, because there's a lot of problem using this. Later on, now we will see what are the issues using a blender section. Okay, so the requirements for the compact section. For flanges of I-shaped rolled beams and channel in flexure, the member is compact if the lambda P is equal to which is equal to BF. So this is the highlight there. The BF. This is the part that we are checking. This BF. That's why it's a BF over 2, because only this part that we will check over the is a ratio of the BF over 2, half of the width over the thickness of the flange, and compared to the 0.38 times the square root of where's my the E. I wait. So it's a function of the E and the Fy. So this is constant for all the steel, the and Fy is you have different strength for different ASTM. As I mentioned earlier, you have different what do you call this strength, like for ASTM A36 is 248, and A wait well, I'll go back. So, there ASTM 992 is a 50 KSI, or is the 348. So yeah, we go back to here. Okay. So the modulus of elasticity over Fy, and then for this for the I shape. Okay. Okay, so this is for the I shape, and for the channel, this will be because it's the extended part is B, so there's no it's the whole width of the flange over TF for channel, and for the web in flexure compression, the member is compact if lambda P is this we only check the web length, which is H over thickness of the web should be less than or equal to 3.76 square root of E over Fy. Okay, so for, as I mentioned earlier, most current ASTM A6W SMC, the W section, these are all the steel's shape description. Shapes have compact flanges for steel strength less than or equal to 345 FPa, except for these sections. So the rest are all compact, and all current ASTM A6W ships have compact webs for Fy less than or equal to 450 MPa. So in the what we call in the ASC manual, there will be if the section is a see there's a F note on the section, then you will know that you wouldn't, or if you want, you can still use it. The non-compact section is just that why do, oh, because for a longer, it really is more what do you call this advisable to use compact, because you can use there's no reduction in the moment capacity. But sometimes when you use a longer beam, you have no choice. So if it's you need to have because it's in the design mostly flexure or the moment forces govern. But for steel, sometimes if you use a longer span, you have to check the deflection. So our topic also is only based on flexure design. But for steel design, you need to do after checking the flexure or the moment capacity, you need to check deflection and the shear capacity of the steel section also. Okay, so check for lateral torsional buckling. The moment strength of a compact shape is a function of the unbraced length. So this is your unbraced length, meaning there's no bracing. So you are, where's the pen? We are using the whole length, the LB. So it's the full length of the span. So LB is defined as the distance between points of lateral support or bracing. So if you have a bracing, for example, the floor, you have a secondary beam. Example, let's for example, this is your floor, this is a plan. Then you have the floor, and then let's say let's change the pen. That's a plan, a floor plan. Then you run your main steel member here along this line. Then you have another one here. So your column is here. Let's say just draw a circle for the support. It's difficult. Yeah, the support is here, the column is here. So if you have a secondary beam, run this direction. So for this part, this the whole there's no secondary beam. So your LB is the distance between point support to support, column to column. But if you have where's my pen? Wait, if you have the secondary beam running across, so means you have a brace. There's a lateral support. So your LB will be where it will be this distance, or it can also be fly brace. So for if you're designing a portal frame, where's the intro? I cannot see other. If you have a oh wait, brace. Portal, you have a portal frame. Okay. So you have a portal frame. Then you have your purlin. So your purlin will be here. So it can act as your bracelet, but it depends. It, okay, so you have this, but it depends on the because the okay for lateral torsional buckling, we check the member or the part of the steel that is under compression. So if you have a portal frame, the moment let's draw the okay, so I it will the moment diagram will be like this. Sorry. Thanks. Okay. So I will like that. So this part will be okay. This okay. This part that under the part of the steel that's under compression is the bottom flange, right? Top flange is and top part. This part is at the top. The top flange is under compression. Bottom is under tension. Here, bottom is under compression. Bottom's under compression. Then, so if for here the purlin is able to raise the top flange, but here your purlin is on top. So the when your moment is when you have a positive moment here, so the purlin will be at the on top and compression is at the bottom. So sometimes we put what do you call it, fly brace, so that you can how to do that? Wait, I'm gonna see. Wait, there. So if you have a C purlin, it's over here. Then we will do oh no, C purlin is running in this direction. So we will do a fly brace from there. And then you can, and then you activate the bottom part. Then it can be considered as then your if you have a fly brace, then uh, your LV part of it. Okay, then that means that your compression part, if the compression is if the moment is this way, moment is this way, so means the top flange is under compression, so you have to brace. But if it's the other way, so you brace the bottom part. But for if you're beam if you're doing a beam that support the slab, so that's why if it's supporting a slab is effectively um the lateral support is considered laterally supported, so your LB will be 0, so you don't need to consider lateral torsional buckling. But you also need to check how the slab is connected to the flange. So if LB is greater than LP, but wait, okay. If these are conditions, if the LB is less than LP, the beam is considered to have full lateral support, and MN is equal to the nominal moment is equal to the plastic moment. So if LB is greater than LP but less than LR, the strength is based on inelastic lateral torsional buckling. If LB is greater than LR, the strength is based on elastic LTP. Okay. We check for lateral torsional buckling. So LP is equal to 1.76 RY square root of E over FY. And these are our limiting lengths for the lateral dorsal. So LR, so this we have to use this very long equation. Okay, so let's see. So if let's see. Okay, so the okay for if your LB, the unbraced length is equal less than the LP, so it's in zone 1, so it will have a full plastic moment. If it's greater than LP, it will be in zone, but less than LR, so it will be in zone 2, and it will have an elastic lateral torsional buckling. And if it's more than LR, it's in zone 3, so elastic lateral torsional buckling. And so for lateral torsional buckling, zone 1, laterally supported, so M and the and CB is a factor to account for the non-uniform bending within the unbraced length LB. And if the LB is greater than LR, so it's inelastic. And so the moment capacity will be FR times elastic section modulus, which is should be less than or equal to MP. And so FR is this, if you notice, if this is a, what you call this, familiar to you, this formula is also used in the column, because if your beam is very long, it will act like a column. So we need to check it will buckle. So we need to reduce it using this FR. This Euler, the Euler buckling equation. Okay, check for lateral torsional buckling. The CB, earlier I mentioned, there's this CB constant, where there's this CB constant. This is the formula for the CB constant. C is dependent on the moment diagram in the unbraced segment. So the expression CB is given in a CP equation 506.1-1. And this is the equation for CP. Yeah, so just these are the how to all the moment that you need to get. But sometimes CB is given, and for what they call this, for should be less than, so you shouldn't exceed 3. But sometimes for conservative, because it's very long, for conservative design, sometimes we use CB is equal to 1. Okay, so the design for plexural members, the procedure in analyzing plexural members, first provide or get the value of Fy from the list of properties of the section, then check for compactness of the member, its flange and web. So if the web over thickness is less than lambda P or lambda R, then it is compact. So if the limit is between this is non-compact and the web, okay, and the web, if lambda R is less greater or WT is double the ratio of the width over thickness is greater than lambda R, then it's a slender. So if both web and flange are compact, use formula from section 506.2. if the flange is non-compact and web is compact, so means uh, is a non-compact section. Use formula from section 506.3, and then if the web is slender, use formula from section 506.5. Even if the flange is compact or non-compact, as long as if the web is slender. Okay, so for design of flexure members, let's assume both flange and web are compact. Then we use the formula from NSCP section 506.2. Then solve for the nominal flexure moment, Mn equals to Fy plastic section modulus. Check for lateral torsional buckling. So your moment capacity depends on the LB. So these just now earlier I discussed the limiting factor and then apply the reduction factor. So after that you apply the reduction factor for ASD for allowable stress design. MU is equal to 3 MN, where P is equal to 0.9, and LRFB is equal to MU over MN, the nominal, the one that you will compute based on this nominal flexure moment divided by the factor 1.67. Okay, let's go for the example. Example 1. So we have this steel section. A36 W450 by 82 steel beam is supported as shown in the figure. So it's a cantilever beam, the support fixed here. And then the beam is fully beam laterally supported and so this is the properties. These are properties of the W for 5082 taken from the table, and let's calculate the dead load. So the dead load of the dead load of the steel is this one, 82 kg per meter. So let's then we convert it to kilonewton. Where is my pen? There, 9.81 over 1,000. So kg multiplied by 9.81, you will get a newton. So you divide by 1,000 so that you can get kilonewton, because our given dead load is in kilonewton per meter. So total, so the dead load plus still dead load. Sometimes we need to for initial design we can ignore the dead load first, because still is very not compared to the to RC. The is a bit quite lighter, so we can add it later on if you don't have the section yet. But now since we have the steel section is given, so we can add the dead load. Okay, so first we determine the laser pointer. Determine whether the section is compact, non-compact, or slender. So B over 2 divide over TF. So you will get this 5.97, and our limiting what call this value is 10.0. 79. So if it's less than, if this the width over thickness ratio is less than 10.79, so the section is compact. Then check the web H over TW, and the limit is 106. So which is equal to how much? 43.23. So it's also the web. So means our beam and the web is compact. Since the flange and the web are compact, the is fully laterally supported, and our moment nominal moment capacity is equal to plastic moment, which is Fy times the plastic section modulus. So from the properties of the section, we can, and it's 836, so the Fy is 248 multiplied by the and we can obtain this moment capacity, Mn nominal moment capacity. So for LRFD, you just multiply by 0.9, and then after we obtain the after we obtain this our Mn in LRFD, you can use formula for cantilever. This cantilever L over 2. We get, if you have the Mu, okay, you have the Mu for cantilever beam is WL WU L squared. And then we just substitute this value, and we can obtain the live load. And then for ASD, we divide by 1.62 factor, and then we can obtain the live load, the maximum live load your beam can take. So that's for example 1. Next, example 2. Determine the available flexural strength of W W350 W350, I think this should be A992. Sorry, there's it should be A992. A typo error. 992. So 992. 992. Yeah. Wait. Erase. So okay, this should be A992. So this still strength is 345 KSI 50. A992 is KSI 50. Oops. Let's go back. Okay, this is 50 KSI 50. Okay, 50. And the FI is 345 under the following support condition. Assuming that CB is equal to 1. So more conservatively, we can use CB is equal to 1. So the loading support condition first is a continuous lateral support. So there's no LTB for this one. Then, okay, for A, we check different loading or support condition. First is laterally supported, so there's no LTB. And then with unbraced length of 6 meters, and then unbraced length of 10 meters. So we obtain the properties of W350 by 1 110. So this 350 is the depth, and then 110 is the weight of the steel. Okay, then continue. So determine first whether the section is compact and non-compact. So based on you just take the ratio of the half of the beam width over, or the flange width over the flange thickness. It's a 6.43 compared to this 0.38 square root of uh, E over Fy, which is 9.15. So it's less than 9.5 for the web, each web, and for the thickness of the web, 28.09 compared to this. The value of this is 9, so it's less than 90.53. So the section is compact. Therefore, it's a continuous lateral support and falling into zone 1. So no instability, therefore will fail in plastic. And so our plastic moment capacity, the nominal moment capacity is your plastics capacity. And then based on LRFD, you multiply it by 0.90, and then this will be your moment capacity based on LRFD. And ASD is divided by 1.67. So you will be this. And so on brace length of 6 meter. So we need to calculate, well, this is very, LP is equal to 1.76. RY, okay, let's do faster. RY, square root of E over Fy. Then LP is equal to 2.67 meters. So if it's, and then your LR, using this long formula, then you, here, the sum, what do you call this, this remember, you can also obtain from the table, and then quite long this formula, then you can obtain the limiting length for LR and L and LP. So if it's 6, so it means is your section is LP is 2.67, 2.67. So it's greater than LB, which is 6. So we are, but less than the LR 9.252. So our moment capacity will be okay. So since LP is LB is less than greater than LP but less than LR, our moment capacity will be this. And since CB is 1.0, so we can use this formula. CB is 1.0. Where is the other? CB is 1.0. This one. And then from here, we can obtain this MN nominal capacity. But should be, you also have to check, it should be less than your MP. Okay, I like that, yeah, there. So based on LRFD, I'll just multiply by 0.9, then you will have your MU, and then ASD, MN is equal to, divided by 1.67. So this will be your moment capacity based on ASD. And okay, so let us see if your brace length is 10 meters. So means LR is 9 point something. Let's see, let's go back. LR is 9.253. So our length now is more than our LB is more than LR. So we will have this FCR formula. We will use FCR for our instead of the FY. We will use FCR, which is 200. How much is our wait? That's now our 348, but it's 345, right? So you can see the capacity is greatly reduced. Becomes wait, the capacity is greatly reduced. You're only using this, and then you're also using elastic section, and that's why your MN will be much lower than uh, the earlier values. So LRFD just multiply by 0.9, and then ASD divided by 1.67. So this will be your moment capacities. If your embrace length is 10. So yeah. Okay. Wow, this to check the LB and the LR, the what do you call this? The formula is quite long. So there's another way we can answer this in how long we take, maybe a few minutes, right? So we can do another checking for faster way using the AISC table. So if you want to do a quick check, let's use the AISC table. So if you go to the AISC table 3.2 section 3.25 page 216, you can see that the LR, the one that we compute earlier. See this LP, how long the formula. Wait, I'll go back to the previous pages. I have to go back. Wait. Where is it? This quite long. LP is still okay. Just a few uh very wait. Oh, there. LB. Go back. Sorry. There. And so this LP is only this, but the LR is this long formula. But actually, if you go to the AISC table, you can get it already, LP and LR. So but it's in a imperial. So in feet, we just we just convert to metric. Or if it's in feet, then multiply by 3 point. Yeah. Yeah, if it's in feet, we just multiply by 3.305, then we will get in meter. So it's 2.67 and LR is 9.46. Let's see if our previous answer is close to this value. What is our LR? Wait, it is 2.67, but here is 9.253. This is more conservative. We have a almost close value, and then to get the moment capacity, we go to table 3.10 section 3125 page 315 of the AISC table, and then below there's a here you just plot the section this 310 350 110 the SI equivalent, in the earlier slides I mentioned, you can get the SI equivalent section. So, but the table is in so you can imperial. So this section is 114 by 74. So it's this one, the one that I highlighted red. So you plot the length. It will be because below this graph, the length is, it will have a length here. Right. I think 6 meters. 6 meter is here. That's why I plot it. There's a line here. I have a line, straight line from below. Then the intersection will be here. So once you get you can get the right here. It's here, actually here. So uh, from the graph, you can get it, the ASD in keeps F this one, the 361 and 521. And what is the earlier answer for 6 meters? Okay. There. 518344. So it's quite close. 518344. 521 here is higher. So our calculation is more conservative. Okay, so that's it. For section C, the table is only until I think 30 plus feet. So it exceeds already. So we're gonna do this shortcut method. Okay, then we go to example 3. W 3 4 3 1 3 4 section is simply supported on the span of 15 meters. The beam is laterally supported at its end and subject 5 so this section, if the section is by uncoupled vector bit over plan of so it is 10.2. This is the rate of weakness of which is the plan is greater than this limit, so it's a non-compact. Our web h over the depth over, or h over depth of the web over thickness of the web is 28.6 and less than this limit 90.5, so it's a compact. So therefore section is a non-compact, and so we will use the nominal strength for RMP is we can still get we will use this for the plastic moment, Fy times plastic section modulus. And then the nominal strength for the compression flange, will have the compression flange will have a local buckling, so FLB. Mn equals to MP minus, this will be the formula. So there will be a reduction in the capacity. So the Mn will be this this will be our Mn 864.6. Okay, so the nominal strength for lateral torsional buckling, let's check. LP is and the LR. So this will be the LP. If our beam is 15 meters, so definitely is longer than LP, and is 12,922, so 12.97. So there'll be our LB is greater than LR, so there'll be it will be in elastic torsional buckling, so we will use FR for our capacity will be reduced to 2 to 8, the capacity. The still the F, we will, instead of using FY, we will use FCR, and so our steel strength will be 2 to 8 MPa multiplied by the elastic section modulus. Okay, so the Mn will be FCR times Sx. So we will use elastic this Sx, the elastic section modulus, instead of the plastic modulus, and this will be the capacity. So LTV will govern. This is what this capacity. This is the capacity that we will use. This will govern, and then this will be the moment capacity that we'll use to calculate the live load. So LRFD multiplied by 0.9 will be anyway, where is it? Then 4185 4815 481.5 kilonewton meter. So using the, because it's a simply supported beam, so we can use this formula for simply supported beam. Supported, you can use this formula, WL squared over 8 equals to the reduced capacity of the nominal moment, and then you can obtain the maximum live load, uniform live load that your beam can take. And using ASD, this will be the nominal moment capacity will divide by 1.67, and based on ASD, this will be the live load. Okay, then we have another checking. Okay, so example 3, we check using the AISC table 3.2 section 3-24 page 215. So you can see these you go back to chapter 17 to obtain the SI equivalent. It's a W114 by 90. So it's this section, this steel section. If you notice, there's a F footnote on the section. Therefore, means earlier we calculate that this section is a FLB, is a non-compact section. So since there is a F footnote, section is non-compact, and then the table, you know, the LR and LP, so it's about 12.6. I checked these 15 meters, so the table exceed the maximum on the calculated capacity. So we cannot use the manual for this example, but we already earlier. So but this already help us a bit when we calculate. We already have LP and LR. And okay, and that so the for further this topic discussion is reference is AIST Manual 15 edition chapter 3 and then NSGP 2015 volume 1 chapter 5 and these two textbook so for your further reading. And so that concludes our discussion. Stop share. Okay. Uh, hello guys. Wala.
Good. Hello.
Yes, that's our that yeah we I only have three examples.
Thank you very much po, Engineer Jeanette po ng Aquino. For the informative discussion. Very hopeful po na para makapasa po sa exam mga fourth year. Um, so let's proceed. May oh, so so let sabi po ba? Right. On behalf of ACES, FEO Labang and the CE Department, we'd like to express our heartfelt appreciation to Engineer Jeanette P. Aquino for sharing their valuable knowledge and time. So, this certificate of appreciation has been recognized and honored by the Association of Civil Engineering Students of EO Alabang for his invaluable contribution as a guest speaker during the event that took place this November 18, 2025. In appreciation of your inspiring and enlightening presentation, ACES is truly grateful for the time, effort, and the expertise that generously shared and left a meaningful and lasting impression on the participants. And of course, kudos to everyone who participate and join this session. So let's give our mentor a big virtual round of applause. Congratulations po. Thank you very much po, Miss.
Okay.
Thank
Thanks,
you very
guys.
much.
ACES. Thanks, ACES, for conducting this tutorial. And thanks to all who participate. And thank you for taking your time or to attend this tutorial session. So I hope I'm able to share a few info and able to help you in your exam preparation. So uh, keep on practicing. So yeah, for you be able to do well in your exams. Yeah, you need to practice. And so I hope you all have a good rest today. Or if you still have, I think you are preparing for your exam and a lot of, I know some of you are preparing for TCs and everything. So I'll pray for all of you to have more strength and time, manage your time to be able to practice and complete all your requirements for your exam. So I wish you all the best and yeah, so hopefully you all be able to do well in your exam. Thanks, guys. Thanks, ACES for having uh, these tutorial sessions.
Thank you po, Engineer Aquino. So before we end po, can we take a picture po at least? So let's open
Okay.
your cameras
Yes.
po. Everyone who are in here. Kurt, pwede pa screenshot na lang. Everyone. Everyone who can turn on their cameras. Hello po, miss. I think nawala po kayo sa camera.
Wala ako.
Yes.
No.
Okay, Kurt, ano na lang, pa-screenshot na lang. Okay.
No.
Smile.
Okay po, okay,
Hindi
ready.
ko marinig.
Wala po kayo on cam po.
Ah, naka-open yung camera ko?
Yes pa, naka-on cam po.
Okay na ba? Hindi pa rin.
Picture na
Ah,
po.
okay.
Vince, Bridge, Marian, on cam po. Ayan, picture tayo guys. Sige, game. Last na kay game. On cam po. Ay, James, on cam. On cam guys, wala mag-on cam. Hello. Sige, picture tayo guys. Okay. Ready? 1, 2, 3. Ay, wait lang. Another picture po. So, ayan, okay, another po. Another one. Bye.
Okay.
Okay. Last one po. Faces tayo guys.
Diba?
Ano mag-aces? Ano?
Ano
Aces,
yan? Ah,
1,
Aces.
ano yung after to? Aces na lang. A. Aces. 1, 2, 3. Okay. Thank you so much po.
Thank you.
Once again, thank you
Thank you,
po
guys.
again, Isaki. Thank you po.
Thanks.
See you later po again.
Ay, yeah, see you later.
Thank you very much.
Hey guys, may tatanong ako. Mag-stop recording na.